pairwise comparable. Care about classification theoretic dividing lines like NTP₂. Another thing that comes out of this is that the incomplete theory of these multi-valued algebraically closed fields is decidable. So there's an algorithm. It's not a complete theory, but there's at least an algorithm that takes a sentence in this language and determines whether or not it holds in all of these sort of fields, or all of these structures. I should, as a warning, I haven't written up things yet, so these are kind of preliminary results that could be wrong if I, yeah, there could be errors. I believe they're true, though. I'm going to try to sketch the proof. And the case where the valuation rings are independent is in my dissertation. So the first step towards this goal of understanding the model theory of like algebraically closed fields with arbitrary valuation rings on them is to consider the case of independent valuations, which turns out to be closely connected to the existentially closed structures in this class. So if you look at the class of multi-valued fields with n, or a field with n independent, sorry, a field with n valuation rings, then the existentially closed fields in that class turn out to be the ones that satisfy three properties. First of all, First of all, they have to be algebraically closed, which makes sense. Second of all, each of the valuations needs to be non-trivial. And lastly, each of the pairs, the valuations need to be pairwise independent. So that's kind of the first step in this whole chain. Right, and that means that the theory of fields with n valuations has a model companion, which is the theory of algebraically closed fields with pairwise independent non-trivial valuations. Let's see, so the way you see this, I'll describe a little bit about how we know this thing is true. So first of all, there's this notion of independent topologies. You could say if you have a collection of n different topologies on the same underlying set X, then you can say that they are independent if whenever you have a collection, you choose a non-empty open set from each of these topologies, then the intersection of all those is non-empty. An equivalent way of saying that is that the diagonal embedding into the product topology is has a dense image. What this kind of means is that you can approximate, like if you choose a point for each topology, you can find a point that is close to all of those. This notion shows up in like Stone approximation, I think is the name of, this is like a well-known classical result that if you have a bunch of different field topologies that are of valuation type, which includes topologies from valuations and orderings, if they are like distinct as topologies and discrete or non-discrete, then you automatically have this independence kind of thing. So that shows up on the next slide. So it turns out in more detail that if you're trying to classify existentially closed fields with n valuations, you have several equivalent characterizations. The most direct one, if you try to just work out what existentially closed means, is that for any irreducible variety, the valuation topology, like each valuation ring is going to induce a topology on the k points of that variety, and you want each of those topologies to be independent. So you need some kind of like strong approximation to hold on that field, on that variety. Another equivalent condition turns out to be that that's holds on the affine line, which is much easier to check. There's this condition. This is saying that there's no non-trivial valuation ring which contains the pair of valuation rings. The last condition is that it's the same independence condition, but on curves. And the way you can see these things are, well, there's a series of implications between these conditions. Sort of a circle, and then, so C prime and C are the Stone approximation things. They say that if you have these valuation rings that are like independent from each other, then the whole set of topologies is independent. For the other steps, maybe I'll just kind of sketch the main things. So A implies B is kind of routine. This is saying if you have a field that's existentially closed, then you need this independence thing to hold. The basic idea is that if you had a variety that is defined over your field K, you can find an extension field of K and extend all the valuations so that the generic point of that variety lives in whatever open sets you want. And you can that way show that there's an extension field of K where all these open sets that you choose intersect each other. And then by existential closedness, that has to happen inside of K already. The only subtlety for that direction A to B is you have to know that non-empty open sets on varieties, sets that are open in the valuation topology, are Zariski dense, which there's a cute proof of that by Arshav in his book on multi-valued fields. It just kind of follows from quantifier elimination in ACVF. For B implies C is trivial. For C, the equivalence of C and C prime on this slide, that's the Stone approximation, saying that if there is no, well, it's some more primitive statement that goes into the proof of Stone approximation. For C implies D, this is going from independence on the independence of the topologies on the affine line, lifting that to curves. There's a way to do that by taking, if you have a curve, you can find some map from the curve to the affine line. You can find a rational function from the curve to the affine line such that all the poles are, so for example, if you have two valuations in play, you want to find like this independence assumption means that if you have a point P and a point Q, actually they live on the curve, then you can find a point that is close to P with respect to the first valuation topology and close to Q with respect to the second valuation topology. And the way you do that, if you know it's true on the affine line, is you find a rational function whose, where every pole is at Q and at least 1, 0 is at P. And then you take a point that is close to 0 with respect to one of the topologies and close to infinity with respect to the other, and you look at its preimages. All of them are close to Q with respect to one topology, and at least one of the preimages is close to P with respect to the other, so you can lift things to curves in that way. The equivalence, going from curves to varieties, is something that you could probably do using like a Bertini type, or I forget which it is, Bertini type argument. There's also more like a direct way to see it, kind of model theoretically, by showing that you only need the case of curves to get existential closedness. Like the key step there is you can prove like a little lemma that if you have a diagram, no, if you have a model M that satisfies condition, the curve version, which is D, and if it's sufficiently saturated, then you can extend, if you have an extension of small algebraically closed multi-valued fields, you can extend a map into this monster model from the smaller algebraically closed field into the bigger one. That's sort of what you need to show existential closedness. You can handle this case of going from one algebraically closed field to a bigger one by breaking into steps that have transcendence degree 1. And to do a transcendence degree 1 step, you only need to use curves. So somehow you can automatically go from the case of curves to varieties. Anyways, this is just a kind of a sketchy outline of why these things are equivalent. And it's kind of nice that if you try to directly figure out what the existentially closed fields are, you end up with this kind of like complicated axiom involving looking at all the irreducible varieties and looking at orthogonal, or looking at independent topologies on that. But it does turn out that you can say it much more concisely by just saying that no two valuation rings induce the same topology, or no two valuation rings have a common coarsening in this set. And so this theory is not the best, or it's sort of okay, but it's missing a lot of useful properties like quantifier elimination, and it also fails to have the independence property. I mean, it fails to have NIP. It has the independence property. The way you can see this is by looking at this sort of map. So if you look at the maximal ideal, if you look at one of the valuations and you look at the maximal ideal, the set 1 plus the maximal ideal, the squaring map is surjective on that. Basically, every number that is close to 1 has its square roots. One of them will be close to 1 and one will be close to -1. So you can define these two principal square root functions, which on my slides I'm calling S1 and well, S1 is the principal square root using the first valuation, and S2 is the principal square root using the other valuation. So we have this map that's the squaring map, or this is the inverse of the squaring map, and that's this like principal square root thing around 1. And basically, it turns out using these functions, you can produce examples of the independence property failing, the examples of quantifier elimination failing. For example, if you look at the rationals with square root of -1 added, of course, the 5-adic valuation on the rationals splits into 2 different valuations on Q with I adjoined. And kind of by using those, using those, you can see that like you don't have amalgamation, you don't have quantifier elimination. Like if you choose, like if you start with a structure that is Q and then 2 valuation rings that both happen to be the normal 5-adic valuation rings, there's like 2 different ways to extend this up to QI. You could either extend them both to be the same thing or to be different from each other. And because these 2 structures are not equivalent, but they have the same underlying structure, substructure that's equivalent, you can't have amalgamation or quantifier elimination. And this kind of goes into more detail about that. Basically, like using these principal square root things, if you take -4, that's 5-adically close to 1, and the 2 square roots of -4 are 2i and -2i, and which one gets chosen by these principal square roots depends on how you extend the valuations. And you can produce 2 different structures on QI where the 2 principal square roots agree or don't agree. You also can break NIP. So if you take any like sequence of infinitesimals or things that are close to close to 0 in both valuation rings, you can produce like this predicate of whether the 2 principal square roots agrees. You can make it be true or false arbitrarily on that set, and you can like make an indiscernible sequence. Basically, this relation of whether or not the principal square root, the 2 principal square roots agree, that relation has the independence property. But at any rate, yeah. So I guess in more detail, what this slide is saying is that if you take a sequence epsilon1, epsilon2 of distinct numbers that are in both of the maximal ideals, you can find you're guaranteed to be able to find an element x such that like S1, like the principal square root using the first of the valuations agrees with the principal square root of x plus epsilon I in the second one, only for odd numbers. And the way you can do that is just by considering, you have to look at a curve that, you look at, like, once you affix the epsilon i's, you look at the set of points x, y1, y2, such that, or up to yn, such that x plus epsilon I equals yi squared. I think you basically you can take some point, by considering this curve, which is irreducible, and using like the independence of the valuations topologies on this curve, you can produce a point where the right things happen. Sorry, it's a bit, I won't go into details, but it's pretty straightforward. I mean, if you try working through the details, you'll see how to do it. One interesting consequence, which I think several people have noticed, apologies to people who have noticed it, because I tried to find where this is written down, but had trouble finding it. Anyways, one consequence of the fact that since we know that algebraically closed fields with independent topologies are not NIP, this actually tells us various things. For example, these 3 conjectures are all equivalent. Well, I think the first one is a conjecture, but this gives other equivalent formulations of it. So the first statement is that every strongly dependent valued field is Henselian. This is kind of like a pretty big conjecture. And strongly dependent is a strong form of NIP. I think we also think every NIP valued field is Henselian, but I'm not sure. Anyways, so that's the first statement. A second statement is that no strongly dependent field defines 2 independent valuations. And the third equivalent statement is that no strongly dependent field defines 2 incomparable valuations, where neither valuation ring is a coarsening of the other. Like the way you can see this, why these things are equivalent. So if you know the first one, if you know that every definable valuation ring has to be Henselian, then when you have 2 different valuations, you would end up with, Actually, I think the implication is A implies C. Huh?
You work with arbitrary expansions of the field. The language is any expansion of the field. What is your language for the...
Oh, yeah, sorry. This is an expansions of the field. Yeah. Yep, that's important. I'm not talking about whether or not you can define a valuation just from the field, the pure field. So I think the implication A implies C. If you know that all valuations have to be Henselian, then as soon as you have two incomparable valuations, you now have, oh wait. Yeah, no, I think it's A implies B. Sorry, I mixed up. Yeah, once you have that, it's a theorem that if you have two independent Henselian valuations on a field, it must be algebraically closed or separably closed. If we're working in a strongly dependent setting, then separably closed implies algebraically closed because you have to be perfect. And then by the previous slide, an algebraically closed field with two independent valuations can't be NIP. So it can't be strongly dependent. So A implies B uses uses this fact. And also uses the fact that you can't have two independent Henselian valuations unless you're separably closed. B implies C, I think you look at like the join of the two valuations. If you had two incomparable valuation rings on a strongly dependent field, you look at the smallest common coarsening of those two valuations, and it will have two independent valuations. So that's B implies C. And then lastly, if you know that C is true, like a strongly dependent field can't have two incomparable valuation rings on it, then you can apply that if you have a field that you want to show is Henselian for C implies A. You look at if it's not Henselian, there would be a finite algebraic extension where the valuation extends to two different valuations, and those two have to be incomparable, so you would get a contradiction to C. So that's why C implies A is true. So that's sort of fun, and I believe A is like part of a...
Can you show that NIP actually is enough in all of them, or is it true?
It's probably, yeah, I believe this is probably also true for NIP. I don't know.
Equivalency, just use NIP.
Well, the catches for A implies B reduced to algebraically closed to get from algebraically closed to separably closed. So it seems plausible that all the previous discussion also works for separably closed fields, maybe. In which case this also would work more generally for NIP, but I don't know that off the top of my head. So I only stated it for strongly dependent fields. Okay, so that's fun. And now, so in the start of the talk, I promised to talk about the case where the valuations are are arbitrary. Like right now, we have a nice theory for an algebraically closed field with a bunch of independent valuation rings because that happens to be the model completion of the theory of fields with arbitrary valuation rings. And so yeah, we are like for that special case of independent valuations, we have model completeness. There's also like a weak form of quantifier elimination. Like earlier, I talked about how quantifier elimination doesn't work, but it works up to algebraic finite extensions in a way that I will discuss later. So how do we generalize this to arbitrary valuations? Let's see. Okay, so here's just like a review of pretty well-known things. If you have an arbitrary field, there's sort of like a tree structure showed up already in the last talk where the valuations on, if you look at the poset of valuation rings on a field, you have, it's basically shaped sort of like a tree. Like if you have any two valuation rings, there is this well-defined join that is the smallest common valuation ring extending them. You can get it by literally multiplying the two rings together. There's also a maximal element at the top that is the coarsest valuation ring, which is just the whole field. And also, if you take a fixed valuation ring, the set of things above it is totally ordered. I don't know what the name of this kind of poset is, so I'm going to call it a tree poset. And now the key point is that if you start with a finite set of random valuations on a field, you can take all their joins, and basically there's this finite, the set of valuations that you get that way is going to be finite. Like you might start with some random valuations, but then you start taking combinations of them and you find the way that they are linked up. Like maybe the first two combine like so, and then maybe the third one looks like this, or they could be arranged in other different ways. But there is, if you have a finite subset S of valuations on a field, then so this structure is, among other things, it's like a semi-lattice with an element 1 that annihilates everything, with an element 1 that's an upper bound. And if you look at the upper bounded semi-lattice generated by a finite set of original valuations, the resulting thing will be finite because upper bounded semi-lattices are like a locally finite variety of structures or whatever. So yes, if you start with S, a finite set of valuations on a field, then you get this like lattice generated by them, or the semi-lattice generated by them, and it is still finite. So now, suppose we start out with some specific poset that has this tree-like structure. So I'll work through an example. Let's suppose that we start out with a poset that looks like, okay, how about there will be a top element 1 and 2 elements below it, A and B. And then below A, there will be 2 more elements, C and D. So given such a poset like this, it needs to be this tree poset type thing. I will define, there's going to be 2 theories. And one of them is going to be the model companion of the other. So the first theory says that it's going to describe a field, and there's going to be 5 valuation rings on it, 1 for each element in this tree. And the requirements are that the top element, this needs to be like a weakly order preserving map. So the valuation ring OA needs to contain OC, and OA needs to contain OD. And OA and OB need to be inside of O1, but also the requirement, this top theory here that I'm defining, aside from asserting that the map is weakly order preserving, we're also going to require that the top thing gets correctly sent to the top element of the whole poset of all valuation rings. So the top valuation ring. Oh, so there's, by order preserving, I mean that like the valuation ring for the element A needs to contain the valuation ring for element D. And like, because A is bigger than D in this poset. So, so I have this example poset here with 5 things, and the resulting theory is going to be the theory of like a field with 5 valuations, 5 valuation rings, and the rings need to be nested in this way. And lastly, well, this thing needs to be the entire field. So that's this first theory that's not model complete or anything. Like arbitrary field, and it has these 4 or 5 valuation rings that are stacked in a prescribed way. And then the model completion of that theory turns out to have the following additional assumptions. Like 1, so in my notation up here, I'm calling T0 is this base theory, and then T is the theory, the model companion. So the additional requirements for something to be existentially closed in this class are it has to be an algebraically closed field. The map needs to, the valuation ring inclusions have to be strictly order preserving. So in this diagram, in this example here of this small poset, the additional assumptions, the additional axioms for this model companion, all of these inclusions need to be strict. I guess OA needs to be strictly contained in O of 1, and O of B needs to be strictly contained in O1. So this is kind of an analog of the non-triviality condition from earlier. And also, there's an analog of independence. So the other condition, aside from being strictly order preserving, is that it has to preserve join, the join operation. So in this toy example I've written, the join of A and B is 1. So an additional axiom is that O of A and O of B have to combine to be O of 1, which is K. So this is saying that A and B have to be independent from each other. So this is an analog of the independence condition. And then similarly, C and D have a join of A. So the other axiom in this example would be, say that O of C and O of D join together to give you O of A. So, so this set of conditions I've written down would describe, for this example, the model companion. So notice that I'm giving a separate theory for each possible poset here. Like for every finite poset with the right properties, you get one of these theories and one of these model companion theories. All right. I don't know if it needs to be finite, but for what I'm trying to prove, I only needed to consider the case of finite ones. I thought there was something about like if you have the theory of a field with like infinitely many valuation rings, each with their own symbol. I thought that didn't have a model companion or something goes wrong, but I don't know for sure. Okay, so yeah, this turns out to be the right kind of generalization of what we were doing previously. Why does this matter? Well, I guess the point is that if you have an algebraically closed field with arbitrary set of valuations, you look at all the combinations and you build up this finite poset, and now you have a model of this model companion. So even though, like, if the thing you started with, you might start out with only, like, somebody might give you an algebraically closed field and it has 3 valuation rings on it, and those 3 rings are C, D, and B here. And it turns out that that structure is not model complete in any way. But as soon as if you take the join of C and D and get this valuation ring A, that after you add that in, now that thing is going to be model complete and have nice properties. So basically, if you have an arbitrary set of valuation rings on an algebraically closed field, by adding in more valuation rings, you can make sure that you do have one of these kind of structures. And those new valuation rings are definable in terms of the original one because they're just like the join of previous valuation rings. And so then how do we prove? Well, so then this theorem I wrote up there, like how do we prove this? One way to think about these structures is to think about them as, well, if we take this toy example of this 5-element tree I've drawn here, to describe this kind of structure, what you really have is you have your field K, and you have 2 valuation rings, A and B, and additionally, on the residue field of A, you have 2 more valuation rings. So you could kind of think of this recursively as you have your original field, and it has a set of valuations on it, and then you have more of these structures on the residue fields. Sorry. So the slide is kind of describing that. For a general poset of this type, if you enumerate the maximal elements, other than that aren't 1, then and you look at the entire tree below each of those elements, it is another one of the posets of these type, and a model of the base theory, the not complete theory, T0, can be thought of as a field K, and it's got n different valuation rings, and on each of those you have another one of these structures for a smaller poset. And the model companion is saying that this top-level valuation rings are independent and non-trivial, and that each of the residue fields is like existentially closed. So to prove this, like one approach at least, is to show this kind of general fact that is sort of like the thing I did initially, except now we have structure on the residue fields. So if you have, for I equals 1 through n, if you have a theory that's model complete, expansion of ACF, and you look at the class of structures that consist of a field with n valuation rings, and on each of the residue fields, you have a structure of the corresponding theory, then the model complete, the existentially closed models of that structure, of that theory, are characterized by the usual things that the field is algebraically closed and they're non-trivial and pairwise independent, in that each of the residue fields is existentially closed among whatever class you prescribe that it belonged to. Like the proof of this kind of thing isn't that bad. Like I can just sketch the rough idea. If you have a structure K and these residue fields K1 through Kn, well, let's suppose we just had 2 of them. And you want to show this is existentially closed, you consider some extension. And then you want to show that you can embed the extension into an elementary extension of K, like into a saturated elementary extension. And well, the rough idea is you use the fact that K1 and K2 are, little K1 and little K2 are existentially closed to pull L1 and little L2 into K1 star and K2 star. You pull up the residue fields all at once, and then you need to figure out how to embed L into K star. But the conditions, you view L as a giant tuple, and you just need to realize that tuple, you think of L as like, for every finite piece of L, you look at the variety that finite tuple from L sits on. And the only conditions you need are that it sits on this variety and that certain like residues of certain coordinates take certain values, which is an open condition. And by the independence of the topologies on varieties, it's doable. Or you can pull, you can kind of use compactness to pull all of L into K star once you've found ways to do the same thing on the residue fields. Sorry for the lack of details on that. Okay, another important thing about these theories, which is how we're going to get decidability, is that you can do amalgamation over algebraically closed bases. This is why you get quantifier elimination up to algebraic covers. So I phrased it here in the general setting where you have these prescribed poset of valuation rings. So if you take an amalgamation problem of 3 models of like not the existentially closed models, but just like arbitrary structures. And if the one in the middle is algebraically closed, you can do the amalgamation. And why is that true? It kind of just involves, you do this by induction to show the amalgamation over algebraically closed bases. You can kind of do this by induction using this weird looking lemma here. You kind of do things inductively from the top down. Like first you amalgamate the fields in the home sort, then you take their residue fields, and you find some common way to lift the residue fields. Then you amalgamate the residue fields inductively. So what this lemma says is that if you have a diagram of fields and the base, like a square of fields like this, and the base is algebraically closed, and the 2 fields on the sides are linearly independent, well, they're independent from each other, like independent if you embedded them into a model of ACF. Then you can kind of glue valuations. Like if you have a valuation on K1 and on K2 and they agree on K0, you can extend it up to K3. And you can do so in such a way that the residue fields are also independent. This lets you extend like all the valuations you want. Like you can get, in this toy example, you can extend OA and OB, and then now you have the residue field of OA. It has 2 more valuation rings on it, and you can use the same process to deal with those. Yep, so that's true. And then, okay, so then that's great because it means that if you have an algebraically closed structure with algebraically closed field with a few valuations on it, regardless of whether or not it's model complete, like maybe it's missing, maybe it's not trivial, or maybe the valuation rings are trivial or something. It doesn't necessarily have to be a model, but you automatically get the fact that it, like an algebraically closed field, its type is already determined by its own local structure. So you can get some kind of like weak version of quantifier elimination from this. I think you get that like you can eliminate quantifiers except for like things that are bounded by like a polynomial condition. It's pretty standard. Another good thing is that these theories are decidable. They're not complete because you can do different things with Q bar. However, like the type space, well, basically by standard techniques, you can still show that these theories are decidable once you have this almost quantifier elimination result. Like to decide if somebody hands you a statement phi and you want to know like is this always going to be true, you can start searching on one side for proofs that it is true from the axioms, and on the other side you can start writing down conditions that pick out pieces of the type space. Like you can, if you want to show that there's examples of where this is false, like if you have a formula phi and it is false in some model, then you can find a finite extension of Q such that if the valuations extend in a certain way to that finite extension, it implies this formula phi is false or something. Sorry, there's It's kind of a standard, I think it's just standard type of argument though. Okay, so this is a weird technical thing. Since the original goal is to show not only that these theories are decidable, but also that they have this classification theoretic property of not the second tree property, there's this weird technical thing that I want to define. So I've mentioned that if you have an algebraically closed field with the structure on it, its type is completely determined. And if you have a field that is not algebraically closed, there could be several different ways of extending the structure up to the algebraic closure. And I'm going to try to just describe a way of doing that randomly so that you get a probability distribution on how things work out. So if you start with a field K, that's a model not of the like existentially closed theory, but just like the T for all part of it. If it's a substructure of like if it's a field with these valuation rings without conditions on them, then, and you have a formula that you want to know whether it's true, and it has parameters in that field, you can start to define this random process. Well, not a random process in a technical sense, but so by almost quantifier elimination, once you've given this formula phi, you can find a finite normal extension L such that whether or not phi is going to be true when you embed K into a model depends only on what happens to this finite extension L. So you pick L, and then you look at all the ways to extend the structure up to L, and you basically take the uniform distribution on them. And you look at the probability that the formula holds based on how you've randomly extended stuff. That doesn't depend on L, because there's a better way to describe it using like Galois groups and stuff. So this defines this random probability measure like on the space of types. So this is kind of an obscure definition, but the main properties it has, it defines a measure on the space of types that K could have when you embed it into a model. This definition is automorphism invariant. Also, there's this nice condition under, basically, if you have an extension of fields, so the way I've written this, I've written like the probability that phi holds given K, because this really depends on the underlying field that you started with. If you started with an algebraically closed field, you've already determined how the thing extends to the algebraic closure, so the probabilities are always 0 or 1. But if you start like with a smaller field, the probabilities can take other values. So in some cases, when you extend the base field, the probability will change. But in certain cases, it does not change. And this last bullet point is describing that. Basically, if this works out much easier in the case of independent valuations, where the only thing you need to assume is that the extension of L, if you have an extension L of K that is relatively algebraically closed, then like this new information from L doesn't impact whether or not the probabilities are true. In the case of nested valuation rings, you have to be more careful. And I believe the thing that I used was that not only is the extension of L over K relatively algebraically closed, but also all the residue field extensions are relatively algebraically closed. And under that assumption, then these probabilities don't change when you add new, like extend the base. The probability that phi holds given L is the same as the probability that phi holds given K. Anyways, oh yeah, so what are we going to use that for? To prove the NTP₂ holds. So without going into the definition of NTP₂, here is a statement that if you know what NTP₂ is, this implies that, that it's true for this theory. So in the theory TP, the home sort has burden at most 2 times n. N is the number of leaves in the tree. Though for the argument I described, you could probably use the number of elements in the tree. Which is worse, but anyways, yeah, so what saying that something has burden at most 2n means that you don't have a certain pattern. So you don't have an array of formulas. You don't have a model where there's this array of formulas that has 2n plus 1 rows and a lot of columns, infinitely many columns, such that every row is k inconsistent. But every path through the columns is consistent. So if this is your like array of formulas, each row needs to have the property that any k sets in that row have empty intersection. But if you take an arbitrary path through the columns, which means you choose one element from each row, every path through the rows, any formula, any path like that needs to be consistent. So this is an INP pattern. And what we want to show is that this doesn't exist, because that is what NTP₂ says. And also it turns out by results of Artem that you don't have to, you can check it on like single variable. You can check it on the home sort. Like you can assume that all these sets, these formulas, are subsets of the home sort. Like the formulas, the element x is a single variable. So here's a sketch of why this is true. So you start out with your crazy INP pattern, and you make it be mutually indiscernible. Like you make every row be indiscernible from over all the others. This is doable. So you make them mutually indiscernible. And then once you've done that, you choose an element that, you know that the paths through the array are consistent. So this first column path, where you hit everything in the first column, that is consistent. So you choose an element A that is in all those sets. And presumably it's not in very many of these sets, because by k inconsistency, it shouldn't be in, it can be in at most k sets from each, k-1 sets from each row. So this point is going to belong to the first column, but not to very many of the other columns. And then you use dp minimality to show, so basically you look at all the reducts to, you have this field with a bunch of valuation rings, but if you look at a single valuation ring by itself, that theory is ACVF, it's NIP and dp minimal and stuff. Oops, sorry, that shouldn't say to do, sorry. But yeah, so it's a property of dp minimality that, so dp minimality is, well, one version of it is just that if you have a mutually indiscernible array that's mutually indiscernible over the empty set, and you name an element from your dp minimal set, you can remove at most one row, and the remaining things are still mutually indiscernible. So you apply that for each of these reducts with the element A, and what you get is that you knock out a bunch of rows, but basically each reduct, each valuation ring, when you name it, you only remove one row. And at least you choose enough rows at the start so that one row is left over. So at the very end, you now have, of this step, you now have at least one row, and it's going to be k inconsistent because it's from the original pattern. The coefficients are going to be indiscernible over A in every reduct. If they were indiscernible, so the point here is that if they were indiscernible in the actual structure as a whole, you would get a contradiction, because since the first formula is true of A, by indiscernibility they would all be true of A, which contradicts k inconsistency. So you have this row, and there it is again. And then you start to use this probable truth thing. So you magically, and this is where I have to sweep a bunch of things under the rug, you find this algebraically closed base field, B, that contains all these like coefficients in the row. And you somehow make it the case that the probability that phi is true given A and little a and capital B is this constant mu that doesn't depend on I. If you can do that, then you know that mu is greater than 0 because so the probability that phi of A be 0 is true is positive because it's already true in at least one model, like your original starting model. So that means that mu is greater than 0, which means that if you look at AB, AB sits inside of your original model. By AB, I really mean the field generated by A and B. I'm not talking about multiplication. So you have your original model M, and you have this thing AAB inside of it. You also have B inside of it. And what you do is you take AB, and you randomly extend the valuations up to AB alg. And then you embed that into another model like N. And then by this probable truth nonsense, you get that with high probability, a lot of these formulas are going to be true. Basically, we have a bunch of formulas. They're probably all like statistically independent. But even regardless of that, what you know is that they all have this, you have this sequence of events, and they all have the same probability mu of happening. You know that that probability is greater than 0. And you have infinitely many of them. So with good probability, more than k of them are going to be true. So you can find some extension where, like, if you take the first k over mu or so, probabilistically reasoning, you can say that you're going to get at least k of these formulas to be true. in this other model that you got, this other model N. And then what you say is, well, I can embed N into M because M is existentially closed, because the space B is algebraically closed. If you made M be big enough, you can embed N into M. That embedding will move A to somewhere else, and the place wherever A gets moved to is now a witness to failure of K inconsistency. So this proof is skipping over some important steps that make it a lot more of a pain, and also explain why I had a factor of 2 in the original bound-on burden. But that's the rough idea, and why I was discussing this probable truth thing, because it lets you make this sort of argument where you can say, oh, well, probabilistically speaking, at least K of the formulas are true if we randomly extend things, and then pull that back into the original model. So then there's a few other kind of open things that I still don't know much about. One of them is just this approach to proving NTP₂ didn't really use this recursive description, where we could think of this theory as being a field with some independent valuations and more structure on each of the residue fields. Maybe it's true that as long as you build up that theory, if you take the theory of a field with independent valuations and some structure on each residue field, as long as the structure on each residue field is NTP₂, then the entire structure as a whole is NTP₂. That might be true. If so, it would explain why this was true in a cleaner way. Another thing I want to know is if you instead of starting with an algebraically closed field, what if you start with a real closed field, or more generally, a DP minimal field? There are cases, so in my dissertation, I showed that if you take a real closed field, and if you have a sequence of a finite set of valuation rings on that real closed field, and if their topologies are all independent from each other and from the order topology from the real closed field, if that set of n+1 topologies is pairwise independent, then that thing is NTP₂. It seems like there's probably a way to generalize the argument to the case where there are relations between those topologies. And there's probably also a way to generalize the thing to any DP minimal field, because we know what those all are. So that's another thing that I want to look into. And then this is probably not true, but something that's for all I know, it could be true, but it's probably not. Maybe it's the case that if you have any, so strong is the analog of strong dependence for NTP₂. It means burden is rudimentarily finite. If you have a strong field with extra structure, is it always the case that you can just add an arbitrary valuation ring to it and still be strong? Probably not, but it'd be interesting if that's true. And if it's not, I would like to know a counterexample. Okay, and these are relevant background papers. All right, that's it.